Okay, video number 2. We're going to continue our review. This one should be fairly short, and then I'm possibly going to post another video of diving into actual wave mechanics. We'll see. So let's finish up with our review of last semester. So last semester we had circular motion, and in that circular motion, anytime that you've got something going around in a circle, there is that acceleration to the inside, the centripetal acceleration, and that arrow looks really not very good. So that centripetal acceleration, we learned that that is mr omega squared, or v squared over r. That's if the particle has a velocity v or an angular velocity omega. And it turns out that the force is equal to MAC, and that's a centripetal force. Let's call it force centripetal. Well, now that we are adding in electromagnetics, we've got a force that's electromagnetic. So we've got a charge and another charge, and then the radius between them. So we can do some stuff with this equation now, since we have our E&M, electromagnetic force, Coulomb's law. So we've got that under our belt, at least this beginning part, and then we're going to be adding in Coulomb's law later. Okay. So I don't know if you guys remember, but if you don't, I'm going to remind you that we had kinematic equations. And we had both linear and rotational. The linear equations, I'm just going to write them out. Our distance is equal to our velocity times time. We also had our distance is equal to our initial position plus our initial velocity times time plus 1/2 our acceleration times time squared. We had the velocity is equal to our initial velocity plus our acceleration times time. We had our velocity average is equal to 1/2, and these are all average things. 1/2 v final plus v initial. We also had v squared is equal to v naught squared plus 2 times our acceleration times the distance delta x. And let me make sure. I think that does it. So then we had the very same equations rotationally. So we had theta is equal to omega t. We had theta equals theta naught plus omega naught t plus 1/2 alpha t squared. We had omega equals omega naught plus alpha t. We had omega average is equal to 1/2 omega final plus omega initial. Omega squared is equal to omega naught squared plus 2 alpha delta theta. And then we had the relationships between linear and our radius. This is our radius from the center of the circle. Our radius is the key to that rotational the rotational equivalence or linear rotational let's say translation. No. To get us from rotational to linear, we use these equations. So x equals r theta. We use v equals r omega. And a equals r alpha. And that gets us back and forth between them. We also have to keep in mind that anytime we're doing something in the rotational mode, that rotational mode has all kinds of ways of looking at it. So we have one revolution. So you can think of it as revolutions or revolutions per minute or all kinds of things like that. Revolutions per hour, per second, whatever, equals 2 pi radians, and that equals 360 degrees. So depending on which of these you're going to want, you can get that through this equation. Of course, 2 pi is equal to 2 times 3.1415 ... And that means 2 pi is equal, I always just do 6.28. But of course it has more behind it. So that's 2 pi, and I am the only person I know who teaches the ghost of radians. When you do something and your length units drop out, so let's do it. Let's do theta equals x over r. I'm just taking this equation right there and solve for theta. You have unit-wise, x is distance in meters and r is distance in meters. So meters are canceling out. What are your units at that point? Well, that's where the ghost of radians comes in, and you are left with radians as your unit. So anytime, let's say x was a number, we can give it the number 25. And we can give r the number 7. And here's theta. So that gives us 25 divided by, oh, we'll say meters, 25 divided by 7 meters, whatever that happens to be. Let's do it. 25, 7 divide, that is 3.57. 3.57. Our meters and everything else canceled out. That gives us radians. Okay. We've got radians now. And what do you do when you've got the ghost of radians, but you really want, say, degrees? Okay, we want to turn that into degrees. Well, if 360 degrees is equal to 2 pi radians, then we can multiply that 1, 3.57 radians, times 1. But that 1, 3.57 radians, that 1 is 360 degrees, and we're dividing by 6.28 radians. So our radians cancel, and we have a number. Let's see if I can do this. 360, I hope so. 6.28 divide, and 204.7. So in my 3 significant digit world, 204.7 becomes 205 degrees. 205 degrees. Excellent. What does 205 degrees look like? Here's our circle. Here's the x-axis, which we typically work from. And we know that if we go all the way to the minus x side, we've got 180 degrees. And if we come all the way down here, we've got 270 degrees. That's our minus y-axis. So 180 plus 15 degrees gives us 205. Is that 15? No, that's 25 degrees. So it's almost 30 degrees. So 205 degrees is 25 degrees more. 25 degrees more than 180 degrees. So this is where we end up. Okay, so that's our theta. Right there. Theta. Okay. So, I'm moving quickly through this review, and we're going to now talk about energy. Energy is in joules, so that's the unit. And when you start talking about energy, the first thing that we discuss is work. Work, and that's a big W, not an omega. And work is in joules. Work happens to equal our force times our distance times the cosine of the angle between them. So you guys are probably, anyone who's had my class before is probably tired well, I don't know about tired, but of seeing this drawing. This is the one I refer to every time. So the angle between the force and the distance that it's traveling, you take the cosine of it, and then you multiply d and f, the magnitudes, together, and that gives you your work. So there's our work. Well, that same thing happens, only now our distance is going to be the same. You're going to still use distance in meters. And our force, though, could be an electromagnetic force, and it could be a charge that is moving. So we'll have that. We talked about gravitational potential energy. So potential energy gravitationally. And we learned that that was mg delta h. So if you start out at a certain height and you get raised to another height, so this is delta h, you now have a potential energy. That object has a potential energy that can be used when it drops back down. And that potential energy is m times the gravitational field at this point times the height that it, so there's its mass, there's the gravitational field, and there's the distance that it's traveling. Okay, well, the same thing goes for electromagnetics. And in electromagnetics, we'll have our potential energy E and M. For now, I'm using that symbol. The delta, technically this is delta PE. So delta PE, that is going to be our charge, whatever the charge is, and our voltage. So we'll have a voltage drop from here to here. So here's, say, V final, and here's V initial, and we have a voltage, and the charge will be going from one to the other. So the very same thing, that distance is, it's not really a distance, it's a difference in potentials, voltage potential, but that's delta V, okay? And anytime you have delta anything, it's V final minus V initial. So delta anything is the final of that thing minus the initial of that thing. Okay. And don't worry if you're not getting this right now, immediately. All of this stuff, we're going to go into depth on. So your test isn't going to be a comprehensive test on the first day. So don't worry about that. Okay, so we're still talking about energy. The work energy theorem is what allows us to go from work, or equate work with energy, and which doesn't really take a whole bunch to do that, but our net work of a potential say of gravity or electromagnetics. That network is will provide us with a change in kinetic energy, which again is equal to the kinetic energy finally minus the kinetic energy initially. Now, of course, and I've said this before, I've beat this horse into your brain, I hope, really well. The most fundamental concept in physics is the conservation of energy. This is the root. So, and I say this knowing knowing things that they didn't know back in the 1600s. So we've studied classical physics, according to Newton. So we've done the classical mechanics. Well, let's say we've done the mechanics, and that is all the forces and Newton's laws. Well, classical physics also includes the electromagnetic mechanics and the laws that go along with that. This is still classical, but yet it's not classical mechanics, it's classical electromechanics, electromagnetic mechanics. So it's all still classical. We haven't got into modern physics yet. But E&M, that's the thing that we are going to get in this second semester. Okay, so it's still part of classical physics. And in that realm, the reason why I'm saying this is because they didn't understand what we now know in modern physics. Including all of the relativity and quantum mechanics and all that stuff. They didn't know that because physics ends up being or is simply the study of energy in all of its forms. A prime example of that is the old thing that, don't worry, we're not doing, but because of modern physics, Einstein gave us this E equals m, the mass of an object, times the speed of light squared. Okay, well, that converts mass into energy. Well, the same thing goes for charges, Q. Charges. That didn't work out. and any other things you might want to think of. So yes, it's physics is the study of energy in all of its forms, and because of that, we can say that the most fundamental concept in physics is the conservation of energy, and the use of that concept is huge. So we can stick an exclamation point on there and box it in and enshrine it in the annals of archives of time for humans' knowledge and all that. It goes down on as our on our tombstone when we're no longer here, I hope. Okay. So that does it for energy. And we're going to now talk about power, which is simply energy per time. So when you're really powerful, person who is powerful, capital P for power, you can do work in amount of time. The smaller the amount of time, the more power you have, because it's inversely proportional to time. The more work you do in a certain amount of time, the more powerful you are. So it's proportional directly to work and inversely proportional to time. So that's power. And the same thing applies, of course, this semester. What other things do we have that it gets conserved? Momentum. Is conserved. And we learned about that. We know all about that from last semester. I'm just reminding you. And what does that mean to have momentum conserved? Momentum P, lowercase p. Doesn't look like it might be lowercase yet, but it is. And P is equal, the final is equal to the initial. And of course that means no force has been applied to our system, and force equals ma, so no A or A equals 0 applied to our system. As long as that's the case, then our momentum is conserved. Along with momentum, we have collisions. We have inelastic collisions, so there's inelastic and elastic. So in an inelastic collision, there's a deformation of the object, colliding objects, one object or both or whatever. So the deformation of the objects requires or forces us to have a delta kinetic energy that is not equal to 0. In an elastic collision, the deformation is minimized or we ignore it. There's always deformation, of course, always friction, entropy always pops into play. That always comes into play, but for all intents and purposes, we can't necessarily measure it sometimes with our abilities at this level of laboratory. So we call them elastic collisions, and elastic collisions have delta E, or delta kinetic energy is equal to 0. So we're going to move next to rotations again slightly. Rotation, because the rotational equivalent of a force is torque, QUE, and that symbol, I like to do this for torque. It's called tau, and torque is equal to the moment of inertia times times alpha. We won't be doing a whole bunch of moment of inertia stuff. Hopefully, we won't be seeing a lot of I in the terms of moment of inertia. The I that we'll be working with is the same symbol, but it'll be current. So that'll be maybe nice. Students usually don't like moments of inertia a whole bunch. But that still exists. That's still a thing. And we also have stability, which we're going to get into in a deeper way. But stability and the notions regarding stability will be explored further, I hope. I'm getting sloppy in my writing. Angular momentum. Which is the rotational equivalent of linear momentum. Angular momentum, of course, is L, and that's equal to I omega. And again, it's something that's going to happen. And I'm not 100% sure which, you'll know it. You'll know it when you see it. One eye will be for moments of inertia, and the other eye it'll be obvious that it's current. So just trust me on that. I hate it when people tell me to trust them, but I'm doing that. I'm asking you to do that. Okay. We did go into, and I'm really glad we did, fluids last semester. And that's kind of important. Similar ideas will show up in the flow of current. Electric current. So that is good that we've done some work with fluids. And we did things like density of fluids. So we've got density. The density rho is equal to the mass divided by the volume. And we'll still have similar things, but instead we'll have a charge density. Instead of a mass density. And that charge density is equal to the amount of charge in the specific volume that we are choosing. So many charges in a volume, and that'll give us our charge density. Also, we did study pressures, and I'm just going to throw out there, I don't know how much we're going to get into it, but electromagnetic pressure, let's just say electromagnetic pressure is a thing. And one of the I don't know, do you guys know about solar winds? Well, that's an electromagnetic pressure. The solar winds are pushing, so they push outward from the sun. There's more to electromagnetic pressure, but a lot of people call it radiative pressure. And like I said, I don't know how much of that we're going to look at. So this part might just be for your own sake. But we have studied pressures, and they are the same pressures. It's just now they're generated electromagnetically. Okay. All right. So what do we have next? We have laminar versus turbulent flow. So laminar versus turbulent flow, this is so big to me in the nature and study of physics. I can't begin to tell you. It's basically what I write about, the changes from laminar to turbulent and vice versa. Let's just say one thing. Electromagnetic fields, or electromagnetics in general, has current flow and definitely has flow to it. So the things that we looked at with flow are, they pertain. They're a part of what we're going to be learning. So it's pertinent. Oh man, pertinent. I hope that is right. Normally I will look something like that up, but you guys are getting me raw here. So that is the end of the review. Review of 1111. Okay, so I may or may not be posting another video. We'll see. It's a lot harder to post videos than to just stand in front of the class and talk about these things on the board. A little bit is required, uploading and all that. But we'll see. I may start some stuff on waves, may or may not. I'll do my best. There's snow outside. Where am I going? It doesn't matter. I'll be fine. I can do stuff. So thank you for watching. And I'm going to try and turn this video off. Come on, please do it for me. Oh no, I can't turn it off. Either that or I didn't record.